Although this is going to be part 4 and probably the last part of my series determining when a time lapse was taken, at least this specific time lapse. And in part 1, I was able to get within a couple of days just by comparing where the sun, the moon, and the stars were between the time lapse and within my skywatching app that I've been developing. In part 2, I looked a little bit further into the analysis of trying to determine what day it was, and I had comfortably narrowed it down to March 26th of 2020, but I wanted to narrow it down even further to see if I could not only determine what time of day it was taken, but with the time of day and the fact that it was around sunset, where it was, and I had estimated 60 degrees north and about 85 degrees east. I did a little bit more analysis in part 3 and I got what seemed like conflicting data, so I stepped back and tried to analyze it a little bit further. In order for me to be able to get a slightly better time frame, I needed to find out roughly where the moon was relative to the sun and to the stars, and for that I wanted to be able to line up each individual frame within that time lapse to my application to be able to move around on the earth and move the time around so that I could line things up as best as I could. So what I did the last little while was to start working on plate solving photographs like this. I added a plate solver mode, and I also added a control that lets me specify a series of numbered frames. In this case, this still represents the number of frames that I extracted from the video, and focusing only on the time lapse, it would have been frame 35 to frame 804. Frame 35 was the sun just before it was setting. Then there was 6 seconds of no action. Then somewhere around frame 300, you could just barely see the moon making its appearance. At that point, I had something to track. And then finally, the last frame was 804. The moon had already set and the stars were already appearing. So this would be Taurus and this would be the Pleiades. So step 1 was to orient the camera and to overlay the stars. So I'm not going to disturb the settings that I have here. These are going to be some of the more final results, but I oriented the camera so that Aldebaran and the Pleiades were more or less lined up for that frame. And then I was able to adjust the time like this here, and I could shift the computed stars relative to where the stars really were. And I've got a slightly unrelated bit of functionality that's related to the plate solver, but at this point the main thing that I was really after was the time. So I've got it set up at the moment. I can zoom in and click on a star, and when I do that, it'll mark the position on that image where that star was located. This will be used for properly aligning the camera later on. And in a separate file, it saves a copy of this frame number with the Unix timestamp. Once I had that recorded, I would move on to the next one. I'm not going to do them all. I'm just going to move to 800 at this point. Right now it's tracking because I've got all of the times already identified properly, but where it would be necessary, I could then realign this properly, register the event, which would save that file number with that Unix timestamp, and I would keep iterating on to the next one. In part 3, I showed how the video that showed the time lapse was not done at fixed intervals, and that the moon and the stars at one point sped up relative to the video. So I went frame by frame for the section of the video that had the greatest amount of fluctuation, and in the middle of this time lapse I went every 5 frames. At the point where the moon was just about to disappear up here at the top, going backwards back towards the anti-sunset moment, moment. I skipped all of those frames because I really had nothing to look at. And then I tracked every 10 frames, I think, of that one, of the sun. So the first step was to identify the time where each of those individual frames was taken. And I just based it on my local time. And as a result, the time offset was not necessarily correct, but individually, frame by frame, it should have represented a reasonably close approximation of the real time that that image was taken. Next thing after that was to try to identify the latitude, because the latitude is required to properly align the camera's orientation with the time lapse. In this case, you could see that the ground is right here at the very bottom. So the person taking this obviously had the camera pointing up here somewhere, and where up here was still had to be determined, but based on the distance between the individual stars and looking at the zoom level and rotation, etc., I figured that it was an altitude of 13 degrees. There was still a little bit of unknown in terms of what latitude it was. What I found interesting was that if I was slightly off on my latitude, the computer would compute a slightly different slope of the stars relative to the angle that the stars took in the time lapse. I could line it up so that the main stars of Taurus line up for one frame, but as I move it around, then they shift out of the circle, and I could see that it was kind of forming a bit of an X where the computed stars would be on one plane and the time lapse was on a different plane. Basing it on that, I would keep adjusting the latitude and the camera's azimuth until I got everything lined up the best that I could. So that is how I arrived at 55.5 degrees latitude. The next thing was to compute the longitude. And so I changed the camera time bias to 0, and I adjusted the longitude until the computed stars lined up relatively well with the stars taken in the time lapse. And at this point, I was able to go from the last frame. It was following fairly well. There's the moon. The moon is slightly off. And if I keep going back a little bit further, the sun lines up. So at this point, I'm fairly close to the longitude of where this time lapse was taken. I needed to narrow down the longitude and the time. And so again, I used the moon in this case. The Earth rotates around the sun once every year. There's 365 days and there's 360 degrees in a circle. So the stars shift their position relative to the sun a little under a degree per day. The moon goes around the Earth once every 28 days and there's 360 degrees for that. So the moon moves around 12 degrees per day. And if you look very closely, you can see the moon moving through the sky relative to the stars. I use that as an indicator to see if I could narrow the longitude and the time of day a little bit more accurately. And this involved a little bit of trial and error. If I look at where the moon is, I computed the moon lagging where the moon really was by about this much of right ascension. And the moon goes backwards relative to everything else. In order for me to move my calculated moon position to where it really was, it would mean that I would have to go earlier in time. And to go earlier in time would mean moving eastward. So I would go 15 degrees at a time. Right now I'm 8.56. So let's go with 15 degrees east. I have to realign everything up again. So I'm going to move ahead a little bit and I'm going to use the stars. So here's where I think Aldebaran is and this is where it really is. So I have to subtract about an hour, more like 50 seconds. I've repositioned my camera further east and I've realigned the time, which is still based relatively on the time where I live right now, but I just offset the computer to make it think that it was taken earlier further east. So now if I come back and look at where the moon is, the computed moon is now closer to the real moon, so I have to do this again. So now let's go 30 degrees. So there's the new setting. And let's go and compare where the moon is again. Definitely closer, but still not quite lined up. Let's try 45. There's the new configuration, and the stars still line up, and the moon is much closer. I think maybe I can get it a little closer even than that. Now keep in mind that the algorithm that computes the moon position has been written trading off accuracy for speed. So I may be looking at the error rate. So a little finagling later, what I did was I adjusted the longitude now to 48.5 degrees east. The stars line up, the moon's right ascension lines up. The declination is not quite right. At least the right ascension is correct. And the sun also lines up. So based on my application, I've got the sun, I've got the moon, and I've got the stars lined up at 55.5 degrees north and 48.5 degrees east. Taken on March 26th of 2020, taken at 12:29 p.m. my time. We can look up online where this is, find out what time zone it would have been in, and from that we could estimate the local time. But at this point, I think that I've done the best analysis that I could on this. Everything that I've done was based entirely on the data that I saw in the time lapse itself. And as it turns out, one of my subscribers in part 2, thinking that I had pretty much claimed victory, sent me a link to the video from the person who took the original time lapse. And at this point, I'm now able to compare where and when it was taken with the original. And sure enough, it was taken at Lasva, Estonia on March 26th of 2020. And I looked it up online earlier, and Lasva, Estonia is at a latitude of 57.86 degrees north, 27.18 degrees east. At this point, I would claim this a reasonable victory. So that's going to be it for this series. I think I'm going to say that this is going to be it for this analysis. I don't think I'm going to work on it anymore. I am going to work on other things, obviously. If you like this video, I would appreciate the thumbs up. Feel free to comment below. And that's going to be it for the moment. Thank you for watching, and I will see you again in another video soon enough. So bye for now.